So I'm dealing with this issue in my house with the air conditioning system, which works through a central furnace that blows air throughout the house. And it doesn't seem to be working that well this summer. And I've realized that is because not enough air is being pushed throughout the ductwork, through the flow registers, into the house itself. So while I've been diagnosing this, I realized it might actually be a good learning opportunity to kind of go over how furnaces work, how fans work, how the ductwork in a standard house works. In houses in Canada in general, you have a central air handling unit in the basement of the house, right? So this air handling unit is essentially a box that has a fan that pushes air, right? And air comes back from the house through the return air ductwork. So you have air coming in, air going out, and as this air is being pushed, it goes through ductwork up to like your second floor or wherever, and it is pushed through floor registers up into your house, and that is what air conditions your house. In the way of this ductwork, you're going to have, over here, you're going to have something called a cooling coil, right? It's a cooling coil has a refrigerant that circulates inside of it, and the refrigerant's really cold. So as the air blows through this cooling coil, it gets colder and it cools your house. And the cooling coil is connected to a condensing unit that's located somewhere outside your house. So this fan can function at a certain pressure drop, right? So the fan is able to generate a certain amount of positive pressure that helps the air push through all that ductwork into your house. Think of it like using a straw to drink a smoothie, for example, right? You need to create a certain amount of pressure inside that straw for that smoothie to travel up. So same idea here. So as this fan is pushing air, it has to go through the filter, through the cooling coil, through these ducts that have elbows and stuff like that. And everything here generates a bit of pressure loss as the fan pushes the air through the system, right? So the filter has some amount of pressure loss. As the filter gets dirtier, the pressure loss increases. The cooling coil has a amount of pressure loss. There's friction loss of the air through the ductwork. And also every time the air has to, like, for example, change direction through an elbow or go through these registers into your room, it loses a little bit of that energy through friction, another phenomenon, right? So what ends up happening is it looks something like this, right? So you have your pressure and the distance. So as the air is traveling through the ductwork, right? So the air is going to start off at some negative pressure on the back of the fan, and it comes up, let's say, as it goes to the fan, gets up to somewhere here, the fan boosts the pressure. As it goes to the filter, it drops down, then cooling coil, it drops down, and then it's going to steadily decrease as it goes through the ductwork. And as it hits, for example, your room is probably at atmospheric pressure, which is zero pressure relative to the environment. So the pressure is going to drop down to zero, right? So the fan has boosted the pressure just enough to boost all that air through that pressure loss into your room. Now, let's talk about what could be the issue, right? So, the original designer of your house has designed your air conditioning system so that all the heat loads that are in each individual room are covered by a certain temperature air at a certain airflow, right? So the air is going through into your room at some temperature T. So let's call this TA, and then your room has temperature TR, right? And let's say this air is flowing at some flow rate Q, right? Now the amount of cooling this air is providing is actually related to, so let's call this cooling equals C is related to the airflow times some constant K times the difference between the room air and the supply air, right? So as you can see, the cooling capacity is dependent on the airflow and is dependent on the temperature differential. Now let's say your air conditioner condensers are working perfectly fine, so your air temperature is fine. If you reduce the airflow, you're going to reduce the amount of cooling that you're able to provide into that room. That's the key here. So let's talk about why the airflow into your rooms might be lower than what's designed by the original designer of the house. Now, this is generally because there's higher than anticipated pressure loss through the duct system. And this could happen for a variety of reasons, right? So as we talked about here's your fan pushing air, filter, cooling coil, ductwork, registers, right? So let's draw that diagram again. So number one, your filter could be dirty, right? When your filter is dirty, it increases the pressure loss across it, and it can reduce your fan airflow, right? So that could be it. There could be some issue with your cooling coil. Maybe there's some buildup of dust and dirt that increases the pressure drop. You could also have some obstructions in the ductwork, or maybe the original designer actually didn't consider the pressure loss across the ductwork properly. So now your fan is actually functioning at a less optimal rate than it's supposed to. So that could be it too. One more thing is all your registers in the floor have something called a balancing damper. Now, a balancing damper is basically like a little thing that you can adjust to increase or decrease the pressure through that floor register, which increases and decreases the flow into that room, right? So you have a room that faces the sun, you want more air to go into that room versus a room that's facing away from the sunlight. So these dampers kind of help you balance that. Now, let's assume there's something causing a change of pressure into your system. Let's talk about how this affects your ductwork, right? So let's draw a little graph here. That's really going to help us. So here's the graph. You have pressure loss delta P on the y-axis, and then you have flow rate. We're going to call it CFM, cubic foot per minute. That's how we measure flow rate in the industry. And we're going to draw something here. We're going to draw what's called a fan curve. So every fan that's manufactured has a curve that it operates on. And this curve is determined through experimentation, essentially. So the manufacturer of the fan will do a bunch of experiments and figure out how this curve looks. It depends on the aerodynamics of the fan. So the fan curve looks something like this usually, right? It's probably not 100% accurate. It looks slightly different for every fan, but the relationship is kind of the same for every fan, right? The higher the pressure the fan has to fight against, the lower the flow gets, right? So let's say the pressure is very, very low, your flow is going to be very, very high. And as you start increasing the pressure, you're going to start decreasing the flow rate. So as the pressure the fan has to fight against increases, the flow that it's able to achieve at that pressure decreases. Now, on your ductwork, it goes something like this. Let's draw it on the pink highlighter. Your ductwork is something like this. No, the pink doesn't even work. I'll just use the blue. Something like this. In your ductwork, as your flow rate is increasing, the pressure loss is also increasing. The more air you're trying to push through that ductwork, the more pressure is being generated because of the friction loss, dynamic losses, losses through the filter, etc., right? Now, the point at which these two curves intersect it's called the operating point. This is where your fan is operating, right? So let's say the manufacturer says that your air handling unit is able to deliver 1,000 CFM at 0.3 inches water column, right? So that what they're basically saying is this operating point, 1,000 CFM at 0.3 inches water column pressure loss. In reality, your pressure loss through your ductwork might be something else because you've changed the dampers, maybe your filter's dirty, maybe the designer didn't consider something. So now your operating point is here. Let's say once you've installed the air handling unit when the house is brand new and it works perfectly fine at this operating point. And in the future, maybe your filters have gotten dirtier. Maybe something broke in the ductwork and it's created obstruction. Maybe the cooling coil is very dirty. So your pressure has actually increased a little bit in your system. So what's happened is your pressure has gone from this So this is your original operating point. Now your pressure is maybe somewhere here, right? Now this new pressure, if you draw a straight line from it, it intersects the fan curve somewhere here, which means if you draw a vertical line down, that's your new flow rate. So your flow rate has decreased by this amount. So now you're actually delivering less air through your ductwork and consequently less air through each of the rooms in your house. And as we talked about before, your cooling capacity is related to the flow rate times some constant K times the room temperature minus the supply temperature. So look, you've decreased your flow rate, which means you've decreased your cooling capacity. So now your air handling unit is delivering less air into the room, which means it's providing less cooling capacity for that room, which means the original design is no longer applicable and probably your room will be a little bit hotter than designed. And in order to fix this, you have to reduce the pressure drop across the ductwork and get it back to nominal. Anyways, hopefully this has been informative for you, and hopefully you learned something.